Hello everybody, this is Mr. Arocena, and on today's video we're going to be talking about standard reduction potentials, which is really just a fancy way of saying how much voltage does this electrode, does this redox reaction create. Alright, so quick definition. Voltage, for those of you who had not taken Physics 12, voltage is the amount of work done per charge. In the context of redox reactions, it's the amount of work done per electron. The higher voltage you have means the more work or the more energy the electron has available. Now, in order for voltage to exist, electrons must flow, or in other words, electrons must be able to move. Okay. Now, voltage cannot actually be measured in individual half cells, despite us having voltage values for individual half cells in our table of standard reduction potentials. But that's actually not entirely true. We can measure voltages as the difference between two half cells. And the reason why we have voltages for all our other half cell in our table is because we always reference them to the hydrogen half cell. So this isn't arbitrarily choice. We arbitrarily define this particular reaction as having a voltage of 0. And then we measure everything based on that. So if you find something, let's say we have a reaction and it has a voltage of 1.5 volts, that voltage is in relation to this one here. Okay. All right. Now, before we get any further, we have to define what is known as the standard state of an electrochemical cell. So this is kind of like our assumed conditions. If our conditions change, then the reactions will also change based on the Chateliers Principle. So our standard state is as follows. So we have a temperature of 25 degrees Celsius. Gases exist at 1 atmosphere. Elements will exist in their standard states at 25 degrees Celsius. So if it's liquid at room temperature, it'll be liquid at 25 degrees. If it's solid, it's solid. We calculate all solutions at 1 molar. And if any of these conditions change, then you can use Le Chatelier's principle to determine how it would affect that particular half reaction. Okay. We don't normally do that though, so this assumption we make here, this assumption that everything is in a standard state, will hold true unless the problem tells you otherwise. If the problem tells you otherwise, then you can use Le Chatelier's principle to kind of determine what will happen. So an example is this. Here's the chlorate half reaction, where we have chlorate undergoing its reduction because it's gaining electrons, and it creates the following: chlorine ions in water. Now, this particular reaction, if the conditions were not normal, so we can then use Le Chatelier's principle to help us figure out what will happen if that were the case. So this will have a reduction potential voltage of 1.39 volts. And if any of the conditions change, then the reduction potential will be different. Okay. So if this forward reaction creates a positive 1.39 volts, and let's say we increase the amount of ClO4 minus, well, based on Le Chatelier's principle, what will happen is that the forward reaction will occur more. And if the forward reaction occurs more, then the standard reduction potential will go up. Because at its normal equilibrium, the standard reduction potential at standard conditions is this. If I change this, if I increase this, forward reaction will increase more, so my reduction potential will go up. Similarly, and I'll change colors. Similarly, if I were to, say, reduce this one, then the reaction would go backwards, and that would cause my reduction potential to decrease. So in this way, we can manipulate redox half reactions to either create more voltage or to create less voltage. And in some cases, we can actually cause certain things to oxidize because it would actually raise their reduction potential higher up on the chart. And we could do the same thing to lower the reduction potential so that we can get two things which would normally not react in a redox reaction to react in a redox reaction. It's kind of neat. All right. Right, so half cell voltages, like I mentioned earlier, are based on their position relative to the hydrogen half cell, which we defined as 0 volts. So for example, this one is, I think this is a copper half cell. Yeah, so the copper half cell has a reduction potential or a voltage of 0.34 volts. And what this means is that this half cell has a voltage that is greater than the hydrogen half cell by that amount. So in order for that reaction to proceed, when this reaction proceeds, it will generate a positive amount of voltage relative to the hydrogen half cell. Alright, so to calculate full cell voltages, we need to just simply add the voltages of each half cell. So if we take the reduction voltage and add it to the oxidation voltage, that'll give us the full cell voltage of the two redox reactions together. Now, one thing to note here is that for the oxidation reaction, you have to remember that oxidation voltages are the opposite sign of the reduction voltages. So before you can put the oxidation voltage into this equation, make sure you switch the sign. Alright, so let's go through an example of this. So let's suppose we have a cell composed of the following two substances: nickel ion, or not nickel, yeah, nickel ion and iron, and then they will combine together to create nickel and iron ions. So when you're given this situation, you have to first identify what substance is being oxidized, so which substance is losing electrons, and which substance is getting reduced, or which substance is gaining electrons. In this case, it's fairly easy to see, because here we've got the nickel 2 plus is going from a 2 plus state to a 0 state, so that suggests that the nickel 2 plus is gaining electrons. That's the only way it can go to a neutral state, which means that the iron must be losing electrons. And identifying which one's being oxidized or reduced is fairly easy, because as soon as you identify one reaction, then the other one must be, whatever's left must be the other reaction. Now we can reference our table of standard reduction potentials to figure out just how much voltage this cell has. So here, our standard reduction potential, if we can find this, it's normally negative 0.45 for the forward reaction, but since this is the oxidation and it's the reverse reaction, this will have a voltage of 0.45 volts. Now the nickel ions going to solid nickel, this will have a voltage of negative 0.26 volts. And we don't reverse that sign because this reaction is the same one as shown in the book. It's not reduced. So the total voltage of the cell is our reduction reaction, 0.26 volts, plus our oxidation reaction, which is 0.45 volts, for a total voltage of 0.19 volts. Now, if you remember from previous lesson, this would mean that this reaction is a spontaneous redox reaction and it would proceed forwards. When this reaction proceeds forwards, you will generate this much energy, or at least the electrons will have that much energy. Okay, so this would be a good example of a battery, because a battery will generate positive voltage. Now let's suppose we change things and we change the cell ever so slightly. So here we will have a cell that looks very similar to the previous one, but it's not quite the same. As you can see, instead of nickel ions, in this reaction we're going to have solid nickel reacting with iron ions to produce nickel ions and solid iron. So now the roles are kind of reversed. So the thing being oxidized is the nickel. So the nickel is going to lose electrons to become nickel 2 plus. Iron is going to gain electrons to become solid iron. Now we do the same thing. The total cell voltage, we just add up the oxidizing voltage and the reduction voltage. So here the oxidizing voltage is going to be, normally this would be negative 0.26, but because it's the reverse, it's going to be 0.26 volts. And here, just read this straight from our textbook, which is negative 0.45 volts. So the total voltage of the cell is going to be our reduction voltage, 0.45 volts, plus our oxidation voltage, 0.6 volts, for a total voltage of negative 0.19 volts. So this reaction would not actually occur because it requires energy. That's what this negative voltage means, is that in order for this reaction to occur, it has to be supplied this much energy. So energy, or I guess voltage slash energy needed to make reaction go forward. And if you contrast that with the previous one, here we had a positive voltage. So what that means is that this is the voltage created as reaction goes forward. So anytime you have a positive cell voltage, that means your reaction will proceed as normal and will actually generate you energy. And if you have a negative voltage, that means the reaction does not proceed, but you can make it proceed if you supply enough energy. You can think of it as this is the activation energy needed to make this reaction proceed. Okay. Now, why would anybody ever want to make a cell like this? We'll discuss that in a future lesson, but you can sort of see that by doing this type of reaction, you can create solid iron. So if you want to create solid iron from iron ions, this is one way you could do it. Alright, let's try another example. Here we have silver ions and aluminum. And the process is much the same. We have to identify what is the oxidation reaction, what is the reduction reaction. So the oxidation reaction is the thing losing electrons. So in this case, I believe that looks like the aluminum. And then the thing gaining the electrons would be the silver. So the oxidation reaction will be the aluminum going to aluminum ions plus electrons. And then the thing being reduced is the silver. It's gaining electrons and going to solid silver like so. Alright, now we'll take a look at what our E voltages are for each reaction, referencing our standard table of reduction potentials. So for the aluminum will generate, it's in your table. The other reaction is shown, so this would be normal. It would say negative 1.6, but because it is reversed, it is positive 1.66. And the silver is fairly high up. Silver plus this will be 0.80 volts. Now, some of you astute people might notice that why aren't I multiplying this voltage by 3? Well, because this voltage represents how much energy is gained per electron. It doesn't actually change whether I have multiple electrons taking part in the reaction. The amount of energy each electron has is still the same. So that's why I'm not multiplying this by 3. When I calculate my cell voltage, again, do the same thing. Take my reduction voltage, 0.80 volts, add it to my oxidation voltage, and this will give me a total voltage for this cell of 2.46 volts. Now this represents how much energy each electron is getting. The fact that this particular reaction occurs 3 times doesn't change the fact that each electron still only gets that much amount of energy. So when you calculate the cell voltage, you only need to count the reaction once. Even if the reaction looks like it occurs multiple times, you only need to count the reaction once. Alright, now how do I go about affecting the potential of a half cell? Well, there's really only kind of one way to do that, and that's to affect or change some of the standard conditions. The surface area doesn't actually affect the half-cell potential, because all changing the surface area does is increase number of reactions, or I guess decrease in some cases. Increase or decrease number of reactions. Each reaction will still produce the same amount of voltage per electron. You just end up having more electrons available. So if you need something to move a lot of electrons, then having a large surface area will do just that. It won't affect the amount of voltage though, so it has no effect on the voltage, but it will cause the reaction to go faster. Or no, I shouldn't say faster, it'll cause the reaction to occur with more frequency. Now, if you change the standard conditions, we discussed this earlier, you can just follow Le Chatelier's principle to determine what will happen. Now, a common theme, a generalization of the reaction is that if my reaction proceeds forward, so if forward reaction increases, then my potential voltage goes up. And similarly, if the forward reaction decreases, then my potential voltage goes down. So if you want to actually increase the amount of voltage you're getting from a reaction, you just have to figure out a way to make the forward reaction occur more often. So either increasing the concentration, increasing the temperature, or maybe in some cases decreasing the temperature if it's an endothermic reaction. But basically, as long as I can make the forward reaction occur more, I can get more voltage. Okay? Now, one thing that's really interesting, and this is something that you guys might encounter, or probably have encountered but haven't really thought about, is that as you use an electrochemical cell, as you use a battery, so as the battery continues to operate, the concentrations of the ions present will change. And generally speaking, the concentrations will go down. And as the concentrations of your reactants goes down, Le Chatelier's principle says that the forward reaction will occur less frequently. As the forward reaction occurs less frequently, then the voltage will actually decrease. Eventually, your difference in voltage ends up reaching a point where the voltage of the reduction reaction is equivalent to the voltage of the oxidation reaction, and at this point your battery is dead, because there's no difference in reduction potential, so there's no voltage being created, so the electrons don't move. Well, they don't move in any meaningful manner. This is why after a while batteries do stop working, because eventually their oxidation and reduction voltages get to a point where they have no more difference, so no more voltage to push electrons around. Alright, your assignment then for this part of the unit is as follows. If you guys have any questions, you know how to contact me.